Pleasure to be here today and talk about this topic. I'm going to go ahead and share my screen. That's my PowerPoint. Let me go ahead and just turn my camera off. I'll turn it back on at the end for Q&A, but might be less distracting if you don't have to look at me, since I'll be doing nothing but looking at my slides and talking to all of you. And let me turn this to full screen mode. So there you go. You guys can hopefully still see my screen. And so I'm going to go ahead and get started. So the topic that I asked to speak about today is the application, excuse me, the application of predictive microbiology to manage food safety risks in last mile delivery. And this is going to be a story of my journey in this world, roughly chronological. So let's just go ahead and get started. The first case study is some work that I did with a company called Jetro Restaurant Depot. And this is unique in a couple of ways. Number one, it's unique in that we actually published this, and you can see the DOI number and the title of the article, which was published in the IAFP journal, the Journal of Food Protection, or JFP. And I'll just tell you a little bit of a story about how I came to do this work. There's a TV station in New York City, not far from where we are in New Jersey, called WABC TV. And they aired two stories in August of 2009 about restaurants that were shopping at Jetro Restaurant Depot, and then loading up their vans with food from this cash and carry operation and driving them to their restaurants. And somehow the news media found out about this. The vans were unrefrigerated. This was during the summer, as it says there on the slide, August of 2009. And they came to me, the TV station came to me to ask my opinion about it. And so I did an interview, as I often do. The joke in my lab is the students know that when I walk into the lab wearing a lab coat, it probably means that the person behind me will be carrying a TV camera or carrying a video camera. And the reason why is that everyone knows that scientists always wear lab coats and they're always in the laboratory, even though that's not really true if you've ever actually met any scientists. So I did my interview with the TV station and then promptly forgot about it. And then I got a call the next week from a colleague who said, "Hey, Don, I'm doing some work for Jetro Restaurant Depot, and they'd really like to talk to you about that interview that you did." And my first thought was, "Oh, crap. I hope I didn't say anything super bad, bashing the company." So I immediately went back and I found the videos on their website and I listened to them. And actually, I did a pretty nice job because I was kind of nuanced. I talked about risk. I talked about the factors that influence risk. These are things that have interested me for a long time. And I actually gave a pretty nuanced answer to some of the pointed questions from WABC. And so I actually began a partnership with the folks at Jetro Restaurant Depot, and they were really nice in funding the work. And so I'll want to talk a little bit about exactly what I did for them. And I adapted all of these case studies to talk about a number of factors. So the first thing that we have to talk about if we're going to be doing this last mile delivery modeling is how many stages are we talking about? In this case, this was the first time I did this. It was very simple. It was just one stage. So we're basically looking at representing the situation when someone shops at this cash and carry operation. They take the food to their van, and then they go to their restaurant, and then they refrigerate the food. So we also have to ask the question, who is the customer for the analysis? In this case, the customer would be the person shopping at Jetro Restaurant Depot, i.e. the restaurant that's shopping there, but also Jetro Restaurant Depot. They cared about risk. They cared about the risk that was going on here, and they were a very progressive company. They made refrigerated, or they make insulated containers available for purchase. I think they give away, or at the time they gave away, free ice packs because they want to help the people that are shopping at their stores to do the right thing. So we have multiple customers in this case. And of course, another potential customer would be, well, what about the TV station, right? Because they want to get an assessment of risk. And so the analysis could also inform them. And then we wanted to use computer modeling to do this. A tool that I often use and that I've used since 2009 and before, all the way up to the present day, is a tool called Combase. Combase is a free modeling program that's available on the web. All you have to do is sign up for an account. And in this particular case, we modeled Salmonella and Listeria. And this figure, or this image on the right-hand side of the slide, just shows the predictions for the Salmonella and the Listeria model, starting at 10 to the 3, which is just the default, and then for a default temperature, pH, and water activity. So you can see the relative growth of the two organisms, and you can see at 20 degrees C, Salmonella grows faster than Listeria, but depending upon the temperature, at some point, Listeria starts to grow faster as you lower the temperature. So again, bottom line is there are some computer models out there. They're free to use. I use them in this analysis. Moving on to the next slide, whenever we're using computer models, we have to make some assumptions. And so in this case, we made the assumption that the organisms were going to be at optimal pH and water activity, and there would be an assumption that the organisms would not undergo lag phase. Now, we know that these are very conservative assumptions. That is, they're what I call fail-safe assumptions. Fail-safe assumptions. They err on the side of safety, and so foods often have a pH that's lower than 7. They often have a water activity that's lower than 1, far away from 1, and organisms may experience a lag. So these are all, like I said, conservative assumptions. Sometimes when we're doing modeling, we have to handle situations where the organism, the model does not extend to the temperature range of interest. And so we have to be able to handle what happens in a situation when we want to know what the organism is doing, but the model doesn't extend to those conditions. Fortunately, in this case, we didn't have that situation. And so we were able to use the computer models for all of these cases. Another really important thing that we have to figure out when we're doing this kind of modeling is we have to make some assumptions about how the temperature is changing. We know from physics and Newton's laws of cooling, which have been around as long as Newton's been around, so quite a long time, that temperature change in response to environmental temperature is not linear. So, for example, the rate of temperature change is proportional to the driving force. So let's say that we have a cold food and we put it into a warm environment. At the beginning of that process, the food is cold, the environment is warm, and so there's a big driving force. And so at the initial phase, the temperature rate rise is very rapid. And then as the food temperature gets closer to the environmental temperature, that driving force, that temperature differential is less. And so the rate of cooling slows. And so we know in actual fact, temperature change is not linear. But we can also make a simplifying assumption, which is really important in this case, is we assume that the temperature change is linear. And that ends up being it's certainly a simplifying assumption, and depending on the situation, it may be fail-safe or not, but it's a reasonable simplifying assumption. And then the third thing, or the fourth thing that the risk managers have to decide is, well, what are we going to allow some level of increase of the population of the microorganism? And of course, you could say, well, we want to be very conservative and we don't want any situation where there's any increase in the concentration or predicted increase in the concentration of pathogens. The problem with that assumption is if you did that, then we would never be allowed to hold food out of temperature control. And this would have tremendous ramifications for, let's say, just your average person shopping at a grocery store. Because if we really wanted to assure that there was no temperature change, we would all have to include refrigerators in our cars. And we'd have to walk around the grocery store with little refrigerated shopping carts, right? Which is immensely impractical. So we know that there's going to be some temperature change when people go shopping. And so there's going to be some predicted increase in the concentration of organisms. And so we have to somehow decide on what is the increase of organisms measured in log CFU increase, what would be what we would allow. And so in this particular case, we made the decision that if there was less than a zero point 0.6 log increase, so approximately 2 doublings, then that would be okay. If it was less than a 1 log increase, but greater than zero point 0.6, we would say that's kind of a yellow light situation. That's a caution situation. We want to be careful, but we're probably still going to say it's safe or acceptable. And then if it was a greater than a 1 log increase, we would say, okay, this is a risky situation. We don't recommend that you follow this. And the idea of coming up with this traffic light, red light, yellow light, green light situation is it would provide feedback to the folks that were shopping at Jetro Restaurant Depot. So the tool that we developed would give them an answer that was red light, yellow light, green light. If it was green light, everything's okay. If it was red light, that's not good. If it was yellow light, well, try to be more careful because next time, if it was a yellow light, next time it might be a red light. Okay. So, first of all, as I mentioned before, we made an assumption of a linear temperature rise. And so we wanted to justify that. And so what you can see, if you look at the panel, the figure on the left-hand side, this is the temperature increase in degrees C as influenced by transport time with data taken from a database. And this is a database that was created by a company called EcoSure. It's available, or it was available, and it may still be available on foodrisk.org, which is a website for collecting useful information used in risk assessment. And what you can see, and what I did was I extracted data from the EcoSure database for prepackaged luncheon meat, which is represented by the white bars, and ground beef, which is represented by the gray bars. And what you can see, maybe not surprisingly, is that the luncheon meat, which is a very flat package with a lot of surface area, the increase is greater than for ground beef, which is typically packaged in a chub, so less surface area to volume ratio. And what you can see, there's wide error bars. And so, what I will say is the EcoSure database is a collection of temperatures, hundreds of temperatures for collected for people shopping at grocery stores. And so this is real life data, not for Jetro Restaurant Depot customers, but for regular, grocery store customers, just consumers like you and me. So, and so this is a robust database with a lot of information. And you can see that there's also wide error bars. And so because this is a database collected from real world experiments done around the country at all times of the year, it's going to rise more in the summer months and less in the winter months. It's going to depend upon how you transport the groceries, if you put them in the passenger compartment or you put them in the trunk, et cetera. And so it does reflect the kind of the messy nature of this kind of data. But what you can see generally, I think you'll agree that those increases are roughly linear, right? They're not exactly linear. They bump around. They got big error bars, but they're roughly linear. So support for our linear temperature rise assumption. Now, what you can see in the middle panel, that's the effective transport time on average temperature. So, and we again looked at just luncheon meat in this particular case, and we grouped the data depending upon the outside temperature. And so, when the outside temperature was the coldest, right, at 18 degrees C, it had one pattern. At 24, a different one, 29 and 35. And you can kind of see a little bit of a trend there that as the external temperature rises, the temperature rise is larger, but they're not really linear. Probably the most linear one is the one at 35 degrees C. But even that is not truly linear. But I think you can agree with my hypothesis that a linear temperature rise is a relatively reasonable assumption. And then finally, what we also did in this case was we collected real world data in our laboratory, which was looking at simulated transport. And so we took the products, we put them into an uninsulated bag, we stored them in an incubator in the food science department here at Rutgers at 37 degrees C, and we used the temperature logger to monitor the temperature over time. And what you can see here is that generally speaking, products that were the open circles represent foods that were in greater surface area packages, and so you can see luncheon meat. Or sorry, sliced cheese, which is the open square, and sliced luncheon meat, which is the open diamond. In those cases, you see this more driving force related temperature rise, where the initial temperature rise is very rapid, and then as you approach the outside or the environmental temperature, the rate slows. But it's still roughly linear on the everything beyond that first quarter hour. And for products that are solid, so this would be ground beef, roast chicken, block cheddar cheese, those rises are all roughly linear. So again, additional support for the idea that a linear temperature rise is a reasonable assumption. And I'm going into a lot of details with this example just because I want you to understand the basic concepts. As we move to the subsequent examples, I'll spend less time on this, but this is a good one just because it's published. You can go back and review my thought processes. You can read the words and read the whole story. But so I'm giving you an abbreviated version here, but it's a useful context for everything else I'm going to say. Okay, next slide. Next case study. This is some work that I did as a consulting assignment. The company's name will be not revealed, so we're going to call this company XYZ. This company has 3 different stages that we wanted to address. They have a picking stage where someone is going through the grocery store picking the food items. It then gets staged. It's held in a staging area under refrigeration control, and then finally a delivery driver comes and picks it up from the staging area and delivers it to the customer. In this case, the customer, not the customer of the store, but the customer for the assignment is internal risk managers within the company, within company XYZ, who want to manage their risk. And in case they need to, they also want to be able to convince regulators that their company practices are acceptable. In this case, we simplified things by only using the COM-based Listeria model, and we made a number of similar assumptions: optimal pH and water activity again, and also no lag again. So these are very conservative assumptions. They bias our analysis towards predicting growth of pathogens, even when they might not happen in the real world. We don't have any situations where we're out of the temperature range of the model, so that's okay. And again, we make assumptions about the temperature change being linear, and we justified that because the company had their own internal heating and cooling data for products according to the way that they handled them, and these rates of change were roughly linear. In this case, we didn't go with the red light, yellow light, green light situation. We just went with red light, green light. And in this case, we said as long as there's less than a 1 log increase allowed, we're going to be okay. And if it's greater than 1 log increase, we're not okay. And that would not be a practice that would be allowed. So let's look at further analysis for this company. So what I built for them was a tool in Excel where the risk managers of the company could input the picking time, the staging time, and the delivery time. And based on their own internal measurements, what was that rate of change when the product is warming up? That is, when it's placed into a warm environment, like during picking. What's the rate of change when the temperature is coming down, like when it's in the staging area and it's been placed back under refrigeration? And then, so basically, if you look at the Excel screen capture on the left, you can see that the green boxes are where the company can plug in the available information in minutes, and then the yellow boxes, these are predicted product temperatures based on our assumptions of linear temperature change. And then the idea is you just take this time and temperature data, time in hours and temperature in degrees C, and you take that information and you just plug it into Combase for the Listeria model, and you make some predictions. What you can see on the right-hand side is a graph from Microsoft Excel of a number of different situations. And so you can see during the picking stage, the temperature rises, and then we place it in the staging area under refrigeration. And depending upon how long that product is there, the temperature is going to go down. Now, we run into, because the rates of change are linear, and they don't really know anything about physics, right? They're just simple linear assumptions. We could have a situation where if we put the product in the refrigerator for too long, the temperature may go down below refrigeration temperature, which is clearly nonsensical, right? That would never happen in the real world, but this is just a simplified mathematical version of the real world. And so we could deal with this in a couple of different ways. We could say, well, when the temperature gets to the refrigeration temperature, then the temperature remains at refrigeration, okay? And then once it goes to delivery, then the temperature starts to rise. Or we could, if we're kind of lazy, we could say, well, let's just imagine the temperature goes lower and lower, even though physics would say that's impossible, and then the temperature rises after that. And so we discussed this with the risk managers in the company, and you can address both situations by making the appropriate formulas in Microsoft Excel. And then what you can see in the bottom right-hand corner is different delivery times in minutes, and then different staging times in minutes, and then looking about whether we allow the dip below refrigeration temperature, or whether we just assume that the cooling rate is slower. That's another thing we could do. We could say, okay, let's just assume that if we're going to overshoot the refrigeration temperature, let's just assume that the product cools slower than the models would predict. And so we can assess these three different situations: the dip, the slow, or the hold, right? Where dip is the yellow, slow is the blue, and cool and hold is the green. And you can see that it really makes very little difference in terms of the modeling predictions, right? So, and most importantly, even for the shortest staging, because remember, staging in this case is helping you because the staging process is starting to cool the product down again, right? But even if you have very short staging and you have very long delivery times, the predicted increases in the concentration of the pathogen are all less than that one log increase that is our risk management standard. And so what this basically said for the company is, hey, we're good with even a 2-hour delivery window. And I think in actual practice, they use a 90-minute window, so they're making it even safer. And it really doesn't matter how long the product is staged, and it really doesn't matter which assumptions you make about the product behavior, because those numbers are I mean, yes, they're slightly different, but they're not different enough to make any practical difference. So that's that analysis. Now we're going to move to a different analysis, which was for the same company. So we're still working with company XYZ, and the previous analysis was delivering cold foods, but this company also wants to be able to deliver hot foods. And an example of a hot food that they want to deliver would be rotisserie chicken. Now, in this case, we're simplifying things and we're just looking at delivery. And again, same customers, right? Maybe internal risk managers within company XYZ, but also maybe regulators who are questioning the practices of this company. In this case, we've changed the model. We're now no longer looking at listeria, which would be unlikely to be in a rotisserie chicken, and instead we're going to look at a microorganism that would survive the cooking process, namely Clostridium perfringens. And there's another tool that's part of the Combase suite of tools called Combase Perfringens Predictor. And I use this tool quite a bit when I'm dealing with cooling deviations for companies or with situations where you have a hot food that's perhaps not being held out of temperature or that's not being held under temperature control. Also, as we did before, we're assuming optimal pH and water activity. We don't need to make an assumption about lag phase because the Combase Perfringens predictor will already account for that. So lag phase is already built in. There's no way to exclude lag phase, which is probably reasonable if you understand the kinetics of spore germination and the microbiology behind perfringens. And I'm happy to talk more about that if you're interested. We don't have to worry about the product being out of temperature range because the model temperature range is consistent. We're still going to make the assumption of linear temperature range. And again, the company has some data, which I'll talk about in a minute. And again, here we're pinning our log increase to an existing standard. So in the United States, the USDA Food Safety Inspection Service is the company that that regulates meat and poultry, and they have a guidance document called Appendix B. And in Appendix B, the agency recommends a less than 1 log increase in Clostridium perfringens as being safe. And so in this case, we're just tying our risk management standard directly to federal guidance, which should help us if we get pushback from regulators who disagree with what we're doing here. So the company has internal data which show this asymptotic cooling that I've talked about before. Again, here, since the food is hot and the environment is cold, we have a rate of decline, and this is this rotisserie chicken that's being held out of temperature control at ambient. And so, and apologies, I've changed degrees C to degrees F. When working with the industry in the United States, a lot of times we use degrees F, but since this is science, we also use degrees C, and that also helps if you're Canadian, since you guys have a sensible metric system up there, which some of us wish we had here. But anyway, I'm always afraid of missing a conversion from degrees C to degrees F, but I've done it enough times now that I'm pretty good at it, and I know the equations in my head, and I can most of the time avoid any stupid boneheaded mistakes. That's why I carry general liability in case I miss a decimal place or miss a conversion. Okay. So what you can see here is that if we run the company's cooling curves through Perfringens Predictor, we see anywhere from a 1.8 to a 3.3 log increase. And these are just for the different cooling curves. If we run that linear curve, which is our assumption, that black curve, we see a 4.7 log increase. So we can say, okay, yes, our linear assumptions are fail-safe. They're conservative. They're going to be okay when it comes to making food safety decisions. Here, we looked at only one delivery time in this particular case for this example of 75 minutes, and then we looked at what is the temperature of the product at the time of delivery. So if the product is at 122 Fahrenheit or 50 degrees C after 75 minutes, we see a very small predicted increase, and that doesn't change much even if we change that final delivery temperature to be 50, 40, 30, or 20. In every case, we are well below that 1 log increase. But then the company said, well, what if we want to push the envelope a little bit? And what if we want to look at delivery times of as long as 130 minutes? So 2 hours plus 10 minutes. So what we were able to do is and so if you look at the diagram that's on the lower left, this is these are predictions from Combase Predictor for different time temperature combinations where the time is the time for linear cooling and the temperature is the product temperature. And what you can see here is I've tried very closely in making some different assumptions and doing some different modeling to get as close as I can to a 1 log increase without going over. So you can see the points in red, that's greater than 1 log. The points in green are less than a 1 log. And just depending upon your pay, and I'm sure there's a way to do this using calculus that's better than my simplistic spreadsheet model, but this was simple and it got the job done. And so what you can see here is, and this is a little bit cleaned up on the right-hand image, here we've divided our delivery time temperature situation into safe and risky. And so basically, if your delivery time and your delivery temperature fall anywhere in that safe region, you have less than a 1 log increase. And if you have anything in the risky region, which is below the blue line and above the orange line, then that's going to be risky or greater than a 1 log increase. And so now the company has a tool that they can look at to say, oh, okay, we can now make an assessment about time and temperature for delivery that's based on science. And so that's the sort of the second, or the third case study, the second one for company XYZ. All right, now we're going to move to another case study. This is a company that we're going to refer to as company ABC. Here, it's a single delivery stage. Same customers of the risk assessment being internal risk managers within company ABC and maybe some regulators. We're back to looking at listeria since this is a cold food that's being warmed up. Same assumptions as before, optimal pH, water activity, and no lag. We don't have to worry about out of temperature range. We're going to make that same assumption again of a linear change. And in this case, company ABC wants to be a little bit more conservative. And so they've said, the company risk managers have said, look, we're going to allow a half a log increase. We don't want to go as high as a log. We're going to manage risk according to a half log increase or better, or greater, or less rather. Okay. So what I did here was to use Combase to create 2 models inside of Excel. And so the company was interested in the question, if I give you a delivery time, what would be the maximum temperature the product would be at that delivery time that would still result in less than a half log increase? And so what I did was I made multiple predictions in Combase, and then I just simply did a linear regression, or essentially a linear regression, or in this case it's curved, but anyway, a regression analysis that shows the relationship between time and final temperature for a 0.5 log increase. And so the green boxes just are screen captures from Excel, and so you can input the time at arrival in hours and minutes, and then what would be the maximum temperature allowed for that to still meet the criterion of less than a 0.5 log increase. But the company also wanted to know the reverse analysis. If I can tell you the temperature at delivery, what would be the time that would be okay and less than a 0.5 log increase? So for example, if the product arrives at 15 degrees C or less, then the model predicts that you can have up to 9 hours and 56 minutes to do that delivery. And so you can see the time and temperature axes for the first analysis and the second are just flipped, but it's the same basic underlying example. And so you plug in the time or you plug in the temperature, that tells you where you are, and then you can figure out where you are on that curve, and that gives you the time for the temperature or the temperature for the time. Okay. Still with company ABC, now we're going to do a 5th case study. And so the case study 4 that we talked about just used listeria. And so the question was raised by the company, Are these models fail safe for other pathogens besides Listeria? Well, the problem is that the COM-based model for Salmonella will only go down to about, reading off the graph here, about 7 degrees C. And of course, good refrigeration temperature is below that. And so how can we predict the behavior of the organism outside the range of the model? And the answer is you can do it relatively simply. And the way that you do it is you can go to the literature and you can say, well, based on the published literature, what is the actual temperature limit to the growth of salmonella? And you can find in the published literature, it's about 5 degrees C. And so the question becomes then, using our computer models, how do we predict what's happening between 5 and 7 degrees C? And the answer is, well, you could just make a simple straight line assumption connecting the lower limit of the model to the lower limit of growth for the organism. Now, one little bit of a nuance here is that we know from years and years of doing predictive food microbiology that the growth rate of the organism changes with temperature. And in fact, it changes approximately linearly with the square root of the growth rate. Now, you can see this is from COM-based, and it's not exactly linear in COM-based, but it's close enough. But we make the assumption that from 7 to 5, it is linear. And so it makes this sort of odd-looking curve, but it's justifiable scientifically based on the published literature and based on the suitability of the model. So when we can use salmonella in these situations, as long as we have this additional component that basically says what the organism is predicted to do between 5 and 7 degrees C. And then we repeated this analysis for a bunch of other pathogens. And so you can see, again, the line here is the 0.5 log increase line, which is what the standard is that the company has decided on, for all of these different pathogens. And you can see this is just solving this by brute force, plugging in multiple scenarios into COM-base and getting the results and then constructing a curve for that. So the original analysis used Listeria, and then you can superimpose on that Salmonella, you can superimpose E. coli, you can superimpose Staphylococcus, Bacillus, and you can see differences for all of these. Now, one thing I want to point out is that generally speaking, the Listeria models are fail-safe. They're not fail-safe for Bacillus and Clostridium botulinum, but we'll talk about that in just a minute. They're generally fail-safe for Salmonella, except when you get above a temperature of about 24 degrees C. And there you can see that the orange dots lie below the blue dots. And you can see it a little bit for E. coli too. And this makes sense, right? Salmonella grows faster than Listeria as you move away from refrigeration temperatures. But again, those differences, those very slight differences are just that, very slight. And so you could either make a correction factor where you build a combined model that would kind of put the Listeria and the Salmonella data that are worst case together, and you can draw a curve through all of that. And that would also be an appropriate situation. But how are we going to deal with situations with spore formers? Well, let's talk a little bit more about that. What we did as a subsequent analysis was to use some other computer models. And so the graph on the top shows time and temperature for a 0.5 log increase comparing COM-based Listeria, which is in blue, and the Skinner-Larkin model, which is a very well-known time to toxin formation model published by Guy Skinner and John Larkin, who were at FDA at the time. And what you can see is that the COM-based Listeria model is fail-safe with respect to Skinner-Larkin. It's not fail-safe with respect to COM-based Clostridium botulinum model, but I think we would agree, or I could make the case that COM-based Clostridium botulinum model is very, very conservative. And in fact, you probably only need to be as conservative as Skinner-Larkin, which is already quite conservative. We can do the same thing for the Juninja model for Bacillus cereus. And you can see here that that Juninja Bacillus cereus model is the Listeria model is highly conservative with respect to that model. It's not highly conservative. It's close to, but not that is not more conservative than the COM-based Bacillus cereus model. But I think the COM-based B cereus model suffers from some of the same very, very conservative assumptions as the COM-based CBOT model. So again, I think we can make the case that generally speaking, the Listeria model will be appropriate for spore-forming organisms. All right. And that actually puts us almost exactly right on time. So let me just recap here. When you're doing this kind of analysis, you need to ask how many stages are you dealing with? And if you're dealing with multiple stages of heating and cooling, that's a little bit more complicated. You need to ask the question, who is the customer? Who is the individual for which we're doing this analysis? And in most of these cases, it's internal company risk managers, but maybe also regulators who might want to push back on what the company is proposing to do. And then the next question is which model to use. And you can see from what I've done here, I like to use the COM-based model because they're readily available. People can check my work. They can make their own modeling predictions. They're robust and generally well validated in the literature. Key assumptions include what is the pH we're talking about, what is the water activity we're talking about, and what is the lag assumption about lag phase. And in every example, you can see that I've made the assumption of no lag phase, which is a fail-safe conservative assumption. I've also assumed that pH and water activity are highly permissive for the growth of organisms, which gives us a measure of safeness or of fail safety in our analysis. I've talked a little bit about some ways that you can handle situations where you're outside the range of the model, which I think are robust and defensible scientifically. Another key thing that I talked about many times is what can we assume about temperature change? And again, generally speaking, we make the assumption that temperature change is linear. And the reason why we do that is that it's a helpful simplifying assumption. It tends to be conservative or fail safe when we're cooling hot foods. It's less conservative and fail safe for warming up of cold foods, but we can also point to examples of the practical observation of cold foods that are warming up. And you can make a case that linear assumption is probably a reasonable assumption based on data of actual food products, even though, yes, it should be, according to the physics, it should be curvilinear, but in actual fact, it ends up being linear or approximately linear in many cases. And then the third or the next point, which you can see we had different answers by different risk managers in this analysis about what is the degree of log increase that is allowed. And we had situations where we're looking at a 1 log increase. We had other situations where we're looking at a half log increase. But again, that's really up to the internal risk managers of the company and how conservative they want to be in achieving their goals for customer satisfaction and workability in the real world. So I've been talking for quite some time. I do like playing around with AI. One of the ways I've played around with AI relatively recently is asking ChatGPT telling it that I'm giving a talk. In this case, on predictive food microbiology and last mile delivery, and to simulate or draw a picture of the audience who's been excited to listen to the presentation and happy to ask questions. And you can see this does maybe not a perfect representation of the folks in the audience. There's probably more of you here than shown here, but these folks are asking questions or getting ready to ask questions. And one of the things that you can, and this is an older version of ChatGPT, and you can see that mostly these people are well-formed and they're not too weird looking. They do have some weird fingers. Fingers are very hard for AI. image generators to generate in some cases. But most of these people seem to have 5 fully formed fingers that look relatively normal. But you can pick out some weird folks there in the audience if you look carefully. So with that, I'm going to stop sharing. And I'm going to turn my camera on, and I am happy to take any questions or comments. See, there's some questions in the chat.
Yeah.
Yeah.
Let's start with those.
Yeah, sure. Delphine writes, very good presentation. Thank you. Based on my experience, the preference predictor tends to overestimate growth for slow cooling curves. Any recommendations on interpretation of growth prediction results or more precise models in those situations? Yeah, it's a great question, Delphine. I guess I would ask, how do you know that it's overestimating growth? So I would want to see the data, and generally speaking, I, I I'm comfortable relying on, for instance, predictor even when it's overestimating growth, just because it's a conservative model and a first case. I don't. My solution is if I'm doing a cooling curve analysis for a company and for instance predictor predicts greater than a 1 log increase, my recommendation to the company is I don't think that you can sell that product. You need to either recondition it or dump it. Um, there are other models out there, but I'm not. I mean, and I guess again, if it was a situation where it really mattered a lot to the company, I would do some more digging and come up with some other recommendations. But generally speaking, I'm comfortable relying on preference predictor, even if it overestimates growth for slow cooling curves. In most cases, the cooling deviations that I'm trying to clear are not 15 hours long. Ellen asks, what are some of the common mistakes when using the models besides the ones that I've mentioned? I think the biggest thing, and I mentioned it, but I'll point it out again. The biggest thing is your assumption about lag phase, and you may, if you're a regular user of Combase, you may have noticed that we've updated the models. I sit on the Combase advisory board and meet regularly with those that control the models. And one of the assumptions we made recently was to turn the default for the model to be no lag phase. And I think we're realizing that the generic lag phase that Combase predicts is probably not universally applicable, and it's probably a result of the conditions that the scientists used that were creating the models that went into Combase. It's the conditions that they used in doing those modeling experiments, and so they are more a snapshot of one set of experiments rather than being universal. Um, Other mistakes, I alluded to this one, but I didn't mention it, call it out explicitly. It deals with the situation with salmonella that I was talking about, where the model only goes down to 7 degrees C. And so I've seen people when the model goes when the model only goes to 7 degrees C, they just make the assumption that if the temperature is less than 7 degrees C, there's no growth. And that's not correct, right? The organism is growing between 5 and 7. You need to address that. So if you want to model the behavior of the organism between 5 and 7 degrees C, or even below 5, if it's below 5, you can say the growth is 0. If it's above 5 and below 7, one assumption you can make is the temperature is 7 and not 5, right? So overestimate the temperature and then just predict the growth that's at, if it's between 5 and 7, just assume that the growth rate is the same as the growth rate at 7. And that's a way around that. But it's absolutely incorrect to assume that if the temperature is below the range of the model, that there's no growth occurring. The model predicts no growth, but that's not the case. So.
Do we have any other questions for Dr. Schaffner? So you can either type your question in the chat box or you can unmute yourself and ask away.
I wouldn't mind asking. Um, as a regulator, sort of the proof of the models is in the testing. So in real world, do you have examples where, I guess, both whether it might have been an issue that arose and then it turns out that in fact they were outside of the model, or have there been cases, sort of outbreaks or diseases, hospitalizations, whatever, that resulted from even when people were complying with what the model predicted, and that gives more guidance on the model?
That's a great question. I don't know of any reported foodborne disease outbreaks for any of these kinds of scenarios, right? But you also have to realize that it may be not detectable by epidemiology, right? Because typically when we have a large outbreak, a multi-state outbreak or a multi-province outbreak, that something goes wrong and then a lot of people get sick. In this particular case, it would require a number of things. The pathogens would have to be there. The growth would have to be better than what the models predict. The person would have to get sick. They'd have to go to the doctor. It'd have to be reported, and it probably would be a one-off. It wouldn't be part of a multi-person or multi-state, multi-province outbreak, simply because there just wouldn't. Because again, it's really a single delivery driver making a single mistake a single time, resulting in illness. And so, one of the things that I didn't talk about here, but I've been involved with a couple of committees for the Conference for Food Protection. For those that don't know, the CFP is a United States organization that helps the U.S. Food and Drug Administration write the FDA model food code. And with these innovative food delivery models, there was some concerns about providing advice to companies. And so we wrote a couple of different guidance documents. And one of the things that we were very clear to include was, just because a company is contracting with a third party delivery service doesn't relieve them of responsibility when it comes to outbreaks. And so we want, part of what's in the guidance is a recommendation that companies be able to pull out that information wherever possible in the event of an outbreak that needed some investigation. So, but the short answer to your question, Simon, is no, those data don't really exist. But if I hear about them, I'm happy to talk about them and incorporate them into my presentation. But I think, generally speaking, we're dealing with foods that are quite safe to begin with. Most of them don't contain pathogens, or if they do, the pathogens are in raw meats, which will be killed by cooking. So I think the relative risk of these practices is posed by these practices is small, but of course, there's no such thing as zero risk.
Thanks.
And just a reminder to everyone that Combase has tutorials if you've never used it, and it's free. Do we have any more questions for Dr. Schaffner? If not, I'd like to thank Dr. Schaffner for taking the time out of his schedule to spend his lunch break with us and for giving us a wonderful talk. I would also like to thank everyone in the audience for attending this event. We now conclude today's webinar. We hope you enjoyed the event, and we hope to see you at the next webinar, which will be hosted by the AQIA on May the 12th. Thank you.
Yeah, and thanks for all the hearts and the claps. I appreciate it, guys.
Thanks, Tom.